All right, so what we're going to talk about now is some of the anomalies that we're going to come across when doing ionic bonding. And the first kind of anomaly or topic that we're going to talk about is how do we deal with metals that make more than one charge? Metals that make multiple charges. We are going to look at the periodic table and decide what charge an ion makes. Now, if they're in group 1, they always make a +1 charge. If they're in group 2, they make a +2. So if you were bonding magnesium with something, you know that magnesium's making a +2 charge because it's in group 2 and it says +2 right above it. These guys all have 2 valence electrons that they want to get rid of. They follow these rules. These guys, they all get rid of 3. So the blue ones just make the 1 charge. That's predictable. That's up at the top. But there are some elements that make more than 1 charge. And those are highlighted in yellow. Now, do you have to actually memorize this? No. You just have to know that there are some elements, and they're mostly in this section, that we actually call the D block. Remember we talked a little bit about sublevels? D is one of the sublevels, and that's this portion of the periodic table. S is another sublevel. These guys, their valence electrons fill the S sublevel, and this section over here fills the P sublevel, and down in the middle here is the D sublevel. You don't really have to worry about that too much. You just have to know that these metals, and remember everything on the left of the zigzag line are metals there, unless it's touching and it's a metalloid. But all these guys are metals, all the way from tin all the way over here to group 1 elements, the alkali metals. So these guys, if they're in group 1, they make +1. If they're in group 2, they make +2. If they're in group 13, they make +3. But the D block and some of these low group 4 or 14, some of these guys here make more than 1 charge. So you just have to know that I've got to check the periodic table to see if it makes more than 1 charge. If you can remember that, just to remind yourself to look back at the periodic table and take a peek if it's an element that makes more than 1 charge, well, you're going to know when you look in the box on the periodic table that it makes more than 1 charge. Here's nickel. Nickel can make a 2 or a 3. Cobalt can do a whole bunch of crazy stuff. Iron can make a 2 or a 3. So if you're dealing with iron, you've got to remember, hey, iron could be one of those elements that make more than 1 charge. Let me check. Let me go back to the periodic table and peek. Oh yeah, I see in the box it can make more than 1 charge. So there's no memorizing here. It's just remembering to peek at the periodic table. And if you see more than 1 element on the periodic table, then we've got to deal with it in a slightly different way. Now, I want to point out that there are some elements that only make 1 charge, even though they're in this same section. So like zinc over here. Zinc always, always, always makes +2. How do you know that? You look in the box for zinc and you see +2. Nothing else. So it makes only 1 charge. So you could memorize that, I suppose. And if you can't remember what zinc does, just look at your periodic table. And silver is in this block here, but it only makes 1 charge. It makes +1. That's it. So you could memorize that. Silver makes +1. Or you could use it over and over again, and every single time you check, and then eventually it gets stuck in your head. Silver makes +1. But it's always there for you. You don't have to go crazy memorizing anything. You just have to remember that if it's an element in this middle section, you've got to check to see if it can make more than 1 charge. All right, so here's the issue. How do you know which charge to use? So if I said to you, mercury's Hg, mercury is going to bond with chlorine. What compound is it going to make? What's the formula going to be? Here's your issue. You look up chlorine. We'll start with chlorine first. You look up chlorine, and chlorine's just a normal everyday element on the periodic table. It's in group 17. You look and see a charge right above it. So you know chlorine always makes a -1. And if we're doing this crisscross business, you know that you would theoretically put a 1 here. But what about the mercury? So you open up your handy dandy periodic table, you take a look at mercury, and here's mercury. And what do you notice when you look at mercury? You see +1, and a +2. So the question is, which one is it? Because they're each going to give you different formulas. So we don't know, is it a 1 or is it a +2? How are we going to know? We'll answer that in a second. Iron. You know iron's going to bond with phosphorus. Phosphorus is easy. All the nonmetals are always easy. Phosphorus is in group 15, which means it has 5 valence. It needs 3 more. It gains 3 negatives. Always. So this is an automatic. The iron is one of those elements that doesn't follow the nice, neat rules that all metals in group 1 or 2 or 13 follow. It's in this section where they could make more than one charge, and iron does. It can make a 2 or a 3. So the question is, how do we know which one to use? And the answer is Roman numerals. We're going to use very few Roman numerals, the very simple ones, but you have to know them. You have to know that an I is a 1. That means it's +1. I is 2. I, you could have 3 at the most, so that's 3. Now, we can't have any more than 3 of the same letters in a row. So we've got to use a different method. Now, I'm going to jump over here and look at V first. V stands for 5. So if you see a V there, you know it's a +5. If you see a V with an I before it, like this, V, I before, that means subtract 1. So it's a 4. If you saw V with an I after it, it's 5, add 1. That would be a 6. So this is really all you need to know. Don't get intimidated by Roman numerals. But the Roman numerals are awesome. It's kind of like a little cheat sheet. If you see Roman numerals, it means you don't have to even look at the periodic table. You don't have to wonder what the charge is, because you automatically know. How do you know which charge to use? It's whatever the Roman numeral tells you. That's the charge on the metal, or the cation, the positively charged ion. It's going to tell you the charge. It's not going to tell you how many are in the formula. You still have to go ahead and crisscross them afterwards. But it tells you the charge, which means you don't have to look at the periodic table to figure out what the charge is. Now note, don't go Roman numeral happy. They're only used with the metals that make more than one charge. They're only used for these guys where there's 2 or 3 or whatever charges in the box. You'll never see zinc with a Roman numeral after it, because it only makes one charge. You'll never see aluminum with a Roman numeral after it, because it only makes a +3 charge. It's only used for elements that make more than one charge. So let's work this out here. We've got mercury 1 chloride and mercury 2 chloride. So we look at the Roman numeral to tell us what mercury is going to do. Remember, we were up here and we were thinking, well, which mercury is it? Is it the +1 or the +2? How do we know which of these two charges do we use? Well, now we know. In this example, this mercury is going to give away 1 electron. It's going to make a +1 charge. How do I know that? Because that's my Roman numeral. Now, chlorine is always over here in group 17. It always has 7 of its own. It always needs to gain 1 more. So chlorine's easy. It always makes a -1 charge because it always takes that 1 extra electron. So if we got a +1 and a -1, well, they cancel out. It's just a 1-to-1 ratio. So it's HgCl. But if we saw mercury 2 chloride, well, the 2 doesn't tell us what to put in the formula. It tells us that mercury is looking to give away 2. It's going to make a +2 charge. Chlorine always makes a -1 because it always takes 1. And you can imagine here that this ratio doesn't work out perfectly. So the mercury is saying here, I've got 2 valence electrons that I want to get rid of. Each chlorine says I can only take 1, but I'll find a friend. So here comes the other one. So there's 1 mercury hooking up with 2 chlorines. That's what we get when we crisscross. So 1 mercury hooking up with 2 chlorines. So take a look at what we found out here. Mercury 1 ends up with HgCl on a 1-to-1 ratio. Mercury 2 is HgCl2. It's a 1-to-2 ratio. Quick note, in this case, there's 1 mercury in the formula. In this case, there's still 1 mercury in the formula. that Roman numeral doesn't tell you how many mercuries are in the formula. It tells you what the charge is. You have to crisscross the charges afterwards. It only tells you what to put down in the charge box. Don't think it tells you what to put down as a subscript. That is not the case. They each have a 1 as a subscript, yet they have different charges. All right, iron 3 phosphide. Let's deal with phosphorus first. Phosphide, remember we changed the ending of all the elements to "ide." Phosphide is really just phosphorus. Phosphorus always makes a -3 charge. So we're going to write -3. Why? Because it's going to get 3 more negative electrons. Over here, iron is still bonding with phosphorus. We changed the ending to "ide." It still gets 3 more electrons, so still makes a -3. The non-metals are easy. They don't do this craziness with the multiple charges. It's only the metals. Now, this iron is a 2 charge. This iron has a 3 charge. It's the charge. This iron's given away 2. Iron's saying, here, take 2, and phosphorus is saying, well, I need 3. Iron's going to say, well, I'll go get some more friends, and so forth. And they eventually work it out so that the ratio becomes, get the 3, put it there, get the 2, put it there. After we crisscross, the ratio is a 3-to-2 ratio. Notice the charge is a 2, but yet there's 3 irons. They are different. They might be the same, it might just be a fluke. But the Roman numeral tells you the charge. It tells you what to put here. Now over here, it's a +3 charge. Why? Because sometimes iron likes to give away 3 electrons, depending on who it's with or what the conditions are. So if iron gives away 3 and phosphorus needs 3, they hook up on a 1-to-1 ratio. FeP. This is a 1-to-1. This Roman numeral is a 3, yet there's only 1 here. This Roman numeral is a 2, yet there's a 3 there. The Roman numeral tells you the charge. I can't emphasize this enough, and the reason I'm emphasizing it is because kids mix this up all the time. Don't do that. All right, lead 2 fluoride. Lead is Pb. Lead's one of those guys that's over here on the periodic table, and it can make a 2 or a 4. This is unusual. Typically, they make 1, 2, or 3. I've been harping on 1, 2, or 3 because I didn't want to mess you up at all. But there are a couple elements that can decide, hey, I'm going to give away all 4 of my valence electrons. And lead can do that, and tin can do that, and cobalt, and a couple other elements can do that. It's not common, but it happens. So if you see a 2, well, you know it gives away 2. But if you see a 4, that means it's giving away 4 valence electrons and making a +4. Fluoride is really just fluorine. We just had to change the ending to "ide." So here's fluorine. It's in group 17. It has 7. It's going to gain 1 more. So we put a -1 in both cases, because in each case, fluorine gains 1. So now that we use the Roman numerals to write the charge, all we have to do now is crisscross. The 2 goes here, the 1 goes there. 1, 2. PbF2. It's a 1-to-2 ratio. Again, the Roman numeral does not match this number. It's not supposed to. The Roman numeral is a charge. Here we got a 4. Fluorine is a -1. Crisscross them. Put the 4 there. Put the 1 there. 1 lead is going to hook up with 4 fluorines. Why? Because each fluorine can only take 1. And lead's trying to get rid of 4. So it needs to send an electron to each of 4 fluorines. And this becomes fluorine -1, fluorine -1, fluorine -1, fluorine -1. All those guys are needed to make 1 lead happy if that lead decides it wants to get rid of 4 valence electrons.